should work. Okay. So yeah, so solving the mystery of the Mima Mounds. So I didn't do all this work by myself. I had help from a couple of co-authors, Taylor and Don Johnson, that you can see there. So what are Mima Mounds? Well, there are these small hillocks that are about 1 to 2 meters high, about 7 to 10 meters in diameter. So you can see a bunch of them here in this Mima Mound field. You can see even more here. This is the Mima Mound Prairie in Washington. This is actually the type site for these features. You can see there's thousands of them in this picture. So that's up in Washington. This is down in San Diego, and you can see all these little mounds. These are also called pimple mounds, and you can see they just look like little pimples on the landscape. Here's a freeway down here for scale. Here, another nice Mima Mound field. This is in the Carrizo Plain, which is maybe a couple hours east of San Luis Obispo. And if you're a geologist, you might notice that the San Andreas Fault actually cuts through the top third of this picture. So this, I'm showing the San Andreas Fault, if you can see my cursor move through. And you can see Wallace Creek here being offset by the fault. But what's really interesting here is not the fault. Who cares about that? It's all these Mima Mounds. And again, you can see all these little pimples in the landscape. Those are just thousands and thousands of Mima Mounds. Here's a nice view of a terrace in Yakima, Washington. And again, you just see these little mounds everywhere. So back to the Central Valley. This is probably where they're known the best, probably where there used to be the greatest number of them. So this is near Merced. And this is LiDAR imagery, and all of these little bumps, these are all Mima Mounds. And this is just a small portion of this much larger area. And so there's a minimum of 100 square kilometers of area through here just covered by mounds. So, thousands, if not millions of these Mima Mounds just in this area. And, oh, you know what? I'm realizing that if I do my share this way, none of the animations are going to work. So I'm going to have to figure out how to do this the right way. So let me.
Yeah, take the time you need. We want to get it right.
Yeah. God, there was a way to do this, and I can't remember.
Are you using two screens?
No, I'm just using one screen. But as soon as if I hit the do the presentation, it pauses the. Oh, maybe if I go back up. Oh, here we go. Okay, there we go. That worked, right?
Looks good. Yep, looks good.
Okay, good. That's a relief. Okay. So this is so in kind of the brown shading here. This shows kind of a general map of Mima Mounds in the United States. So you can see pretty much the West and the central US has Mima Mounds or features that look like Mima Mounds. And in fact, Mima Mounds are found on all continents except Antarctica. Okay, so these are pervasive throughout the world. So here's another view of them, and what you'll notice, so a couple interesting things. So first of all, you'll notice water accumulating here in between the mounds. And so these are vernal pools. And as some of you may know, vernal pools are kind of rare habitat now in the Central Valley. They used to be much more pervasive. And they are habitat for endangered species like the fairy shrimp. Now, another thing you might notice about this picture is that there's a sharp dividing line between these Mima Mounds on the right and then this flat surface on the left. And you might think, well, that's kind of weird. That can't possibly be natural, and you'd be right. Because a lot of these Mima Mounds existed in areas that were also prime land for farming and agriculture. And so when farmers moved to the Central Valley, they invented this thing called the Fresno scraper. And this was a special device that was designed to basically level the fields and destroy the Mima Mounds. And so this is a view of the Fresno scraper at work. Obviously not on a Mima Mound, but you get the idea that if you're a farmer and you wanted to level your field, this is how you would do it. Now, of course, the big question that you should all be asking yourselves is, how were they created? The first person to actually publish on this was Commodore Charles Wilkes. He was the commander of an expedition kind of sponsored by the US Navy. This was in the middle of the 19th century, where they had this big expedition throughout the Pacific Basin to kind of map things and see what was going on. This was, during the early years of the United States. Most of the action was happening in the East. They didn't really know what was happening in the West. And so this expedition was to explore the Pacific Basin. Now, one of the kind of the interesting outcomes of this expedition was that they discovered Antarctica. But even more interesting than that was that they went to check out some Mima Mounds. The Commander Wilkes had heard about these strange features near Puget Sound, which is in Washington State. So they made a special detour to the Mima Mound Prairie, which I showed you a picture of earlier. And he had his men dig into 3 of them to try to figure out how they formed. And you can see down here at the bottom right, there's kind of a picture that he drew in his report. And after digging into these things and thinking about it for a bit, he determined that they bear the marks of human labor and are such an undertaking as would have required the united efforts of a whole tribe. So he thought that these had been or were being created by the indigenous people there, possibly as burial mounds. Other hypotheses that emerged since then. So Louis Agassiz, who discovered the ice ages, thought that they were the nest of a species of sucker, which is a type of fish. The brother of Alfred R. Wallace, who some of you might remember as the Dakota Scar Revolution, his opinion was that they were formed by innumerable rills that issued from the retiring ice sheet. And there have been a bunch of other hypotheses that have been proposed. So for example, that these Mima Mounds are formed by wind erosion, by the venting of gas, subsurface gas, by artesian pressure being released, by earthquakes, giant roots, and of course, aliens. So this is a reference I found. This is a book called Extraterrestrial Intervention. And there was a short chapter or article in there called The Mima Mounds. Unfortunately, I wasn't able to get a copy of this. I'm sure it would have been compelling reading. Another theory that came about in the 1940s was called the fossorial rodent hypothesis. And so, and this hypothesis was based on kind of the basic observation that on top of these Mima Mounds, so if you can see my cursor, I'm kind of outlining one of these Mima Mounds, there's ample evidence of gopher activity. If you've ever had gophers in your lawn, or if you've noticed gopher activity on a hike, you're going to recognize kind of the spoils of this gopher activity. Gophers, of course, are fossorial animals, which means that they live in the soil, and they dig these extensive burrow networks. Some of these, they dig some chambers where they store food. They dig other chambers for nesting. but mostly, mostly what they're doing is they're constantly burrowing because that's how they get their food. So they're eating the below ground plant parts, the roots and so on. And so they constantly have to dig for food. And so the idea is with this hypothesis is that these mounds, one of the observations was that these mounds seem to form in areas where there's a hard pan below the soil. So we see, so kind of in orange here, we've got a layer of soil over this hard pan. And then we've got kind of a little vegetation here to show you the perspective. Now, the thing with hard pan, so hard pan is a layer in the soil that develops over time that kind of in the most extreme case is like a layer of concrete in the soil. And so the idea is that when it rains, the rainwater is unable to infiltrate through the hard pan, and you get this perched water table that essentially saturates the soil. Now, if you're a gopher living in that soil, you get saturated too, and you drown. So clearly, this is a bad situation for gophers. And so the hypothesis was that the gophers have somehow figured out that if they push the soil into mounds, when it rains, there will be a part of the mound, the top of the mound will remain dry. And that way, the gophers will live to see another day. And so the creation of these mounds then is just a response to seasonally saturated soils, and that's what underpinned this theory that the gophers had created the mounds. There we go. So we know that gophers can push soil downhill. So this is a picture I took. You can see there's a lot of gopher activity. There's these gopher tunnels here on the side of this road cut, and you can see just all the soil being pushed out of these out of the tunnels. And when you think about it energetically, of course, it makes sense for gophers to push soil downhill rather than uphill. And so one of the kind of the key questions in this hypothesis was, well, do gophers actually push soil uphill? And so there was an interesting study that was done where they had set out a number of magnetic tracers, so kind of represented here by these black dots, throughout a Mima Mound field. And so they just set them out, and they came back maybe a year later to figure out, where these tracers had been moved. If it was, if the gophers were able to push the soil uphill, you might find that these tracers also had been pushed uphill. So that was kind of the idea. So, so they came back a year later. They used a metal detector to figure out where these tracers were, and they came up with some very interesting data. So on the x-axis is transport distance, and on the y-axis is elevation. So the transport distance here, so positive numbers, that's distance, that's transport towards the center of the mound. Okay, so which is here in shown with the dashed line. And then negative numbers, that's transport distance away from the mound. So what we see is that at lower elevations, so that means further away from the center of the mound, the tracers were pushed the furthest distance towards the center. Okay, and then as you go higher in elevation, which essentially means as you go further up the mound, or closer to the center of the mound, transport distances decrease. Okay, so the further away these tracers were from the mound, the further they were pushed towards the center of the mound. And there was one tracer that was pushed away from the center of the mound, and that was the one that had started off at the top of the mound. Okay, so we see this net transport of soil, of tracers and soil towards the center of the mound, but that's balanced somewhat by soil at the top of the mound is being pushed away from the center of the mound. And of course that makes sense because if you didn't have this data point right here, it would suggest that mounds just get infinitely taller and taller and taller. So there's a balance between soil being pushed towards the middle and soil being pushed away from the middle. So just to kind of summarize what that means kind of more graphically, so the arrow represents the distance that the soil was transported. And so again, kind of near the bottom of the mound, you have a greater transport distance, but as you get towards the top of the mound, transport distances decrease. But we see that the soil is pushed uphill towards the mound center, and that soil is pushed a distance inversely proportional to elevation. And soil at the top of the mound actually gets pushed away from the center of the mound and towards kind of downhill. And another interesting result from that tracer study was that even tracers or soil that were at distances from 5 to 7 meters away from the mound were still being pushed towards the mound. So that means that even gophers that were 7 meters away from the mound were still able to orient their pushing activity towards the center of the mound. And so what this suggests then is that gophers can sense high spots from far away. Okay, so what have we learned so far? Well, so first of all, we know that gophers live in the mounds. We also have evidence that gophers can maintain the mounds. So that tracer study, all that tracer study showed was that the gophers can maintain the mounds, but can gophers actually build the mounds? Now, it turns out the creation of these mounds seems to take decades to centuries. And so it's very difficult to convince a graduate student to grab a lawn chair and just sit out in the middle of the field for 50 years and make measurements. And so one way to speed up time is to do that with a numerical model. And so that's what I did. So what I did is I created an artificial landscape, a synthetic landscape, and I populated it with synthetic robot gophers. And I taught these gophers how to behave. And so the gophers followed these rules. So first of all, the gopher looks around and looks for the nearest high spot and pushes soil towards that nearest high spot. Now, this part's a little tricky because you can imagine that if you're a gopher and you're just sticking your head out of the ground, you may not see this big mound over here because your view is blocked by the smaller mound. So I had to basically calibrate gopher vision, if you want to think about it that way, such that the high spots, well, so the issue, yeah, is that high spots further away are less likely to be sensed. And so there's this weighting function whereby this may be the actual elevation, but this is what the gopher sees. And again, this has to do with the fact that, their vision is going to be blocked because they're just sticking their head out. Gophers don't like to walk around the surface because they're easy prey. They have terrible vision. They don't see very well. They don't like being on the surface. And so they just stick their heads out of the holes. And so if you're sticking your head out of the hole, you're just going to see the nearest mound. And so these robot gophers, I had to adjust their vision to account for that. So the elevations in the model are weighted according to where the gopher is. And it turns out that the weighting function actually controls the diameter of the mounds. So the further they can see, the larger the mounds, and the more kind of nearsighted they are, the smaller the mounds. The other rule that these gophers had to follow was that the transport distance is inversely proportional to elevation. So the distance that they push the soil depends on where they are on the mound. And again, you know, that if you recall the data that I showed you, it showed that there was a strong inverse relationship between transport distance and elevation. And then there's also a gravity rule, and the gravity rule accounts for all the other processes that might transport soil, and these are all kind of subsumed under the kind of the soil creep label, and soil creep generally just moves soil downhill. So in addition to gophers moving the soil around, there's also soil creep pushing soil downhill, kind of in a chronic fashion. Okay, so just to sum up what these rules look like graphically. So if the gopher is far away from the mound, the gopher or the Mima mound, it's going to push the soil a pretty good distance. If the gopher is already a little bit higher in elevation on the mound, that transport distance is going to be a little less. And then there's soil creep always happening in the background, pushing soil downhill. Okay, so gophers are pushing soil uphill, soil creep is pushing soil downhill. And so, you know, as you can imagine, over time you get to a steady state. So this is what the numerical model looks like in cross section. So this is just a profile. And so the model space is initially roughened with just a little bit of topographic noise. So it's essentially a flat surface roughened with this random topographic noise. The model domain that we're looking at here, so this is 10 meters horizontally and 1 meter vertically. And I'm gonna focus your attention on this little bit of roughness on the soil surface right there. What's gonna happen is, because this spot is just a little bit higher than the other spots, the gophers are gonna be moving the soil towards this spot. And you're gonna see that over time, this little hill, you know, the expression making a mountain out of a molehill. Well, it's just the opposite here. A mountain is going to be formed out of this little hill here. Keep track of the time here on in the right upper corner. It goes slow for about the first 50 years, and then it speeds up. Okay, so here we go. Okay, so I'm going to pause it for just a second. Actually, I'm going to back it up. Okay, so you see this main mound forming in the middle, but there was this kind of smaller mound here that also formed. You know, and again, this has to do with the fact that sometimes the gophers can't see the big mound because it's being blocked by the smaller mound. But watch what happens to this smaller mound over time. So after about 500 years, we reach a steady state situation. Oh, and it just disappears. But what you'll notice is that smaller mound disappeared, and essentially what happens is it got cannibalized by the larger mound, and this will become even more clear in the next. And okay, so now this is, we're looking at this from above. This is exactly the same model as I showed you just a second ago, but now it's the entire model space, and we're looking at it from above. So we have distance on both the X and the Y axis. If you're wondering why this is in decimeters, this is one of those things where it seemed like a good idea right when I was starting to code the model, and then 2,000 lines later, I realized it was a dumb idea, but it was much too late to change. So this is basically a 40-meter model space, so 40 meters on each side. And elevation is represented by contour lines. So if you've looked at a contour line before, like a topographic map, you'll understand what this means. But the colors represent areas of equal elevation. And so this is right at the beginning of the model, and so everything's just kind of flat. Again, it's just this surface roughened by topographic noise. But pretty quickly, you'll see kind of mound things start to form. So I'm going to get this started. Okay, so I'm going to pause it here. And hopefully now you can see the contour lines a little bit more clearly. So clearly red is the high elevation, and then as we transition through the greens and the blues, we get to lower and lower elevations. So you can see the mounds already starting to form. Of course, everything's kind of square because that's just how things work in a grid. Soil can only be moved in 8 directions. So it starts off looking a little bit wonky and a little bit squarish, but they round off. Okay, so that's after about 40 years, and then again it's going to speed up. Okay, so I'm going to pause it here and I'm going to highlight something. So you'll notice that some of these mounds, like this one right here that I'm showing with my arrow, this one right here, they're being pulled apart. They're being cannibalized by the adjoining mounds. So this mound here is essentially being torn apart by these 3 mounds. This mound right here is being cannibalized by its 3 neighbors. This mound right here being cannibalized by its 3 neighbors. So as you watch this, you'll notice that there is a kind of a consolidation whereby the weak mounds are being cannibalized and consumed by the larger mounds. And it's kind of weird to be talking about the mounds as if they have agency. But in a way they do, because gophers only live 2 or 3 years, but it takes decades to centuries for these mounds to form. And so, so these mounds actually do kind of take on a life of their own in a way. They live much longer than the gophers do, and they keep evolving long after each of the gophers has died. So that was so I'm go back to this just to point something out. It's so okay. So there you it's so annoying that the player just okay. So you'll see the year 860. So it's taken about 1,000 years for this Mima Mound field to fully develop. And so again, that's way longer than the lifespan of an individual gopher. Okay, so I'm going to go back to this. Great, it worked. So now if I take my model results and I do a pretty hillshade map on it, it looks like this. Which looks pretty close to a real Mima Mound field. So for example, here is, you can see a Mima Mound field conveniently in black and white. And, it's undeniable that the computer model has created something that looks like what's happening in the real world. And I can even I can flood the model a little bit. add some water, and boom, we have vernal pools that are also forming in between the mounds. So this cannibalization of mounds deserves a little bit of extra attention, because when I first saw this happening in the model, I didn't believe it. I thought, well, this is some weird model behavior that cannot possibly be real. Nobody had ever observed this happening in the real world. Nobody had ever hypothesized that it happened in the real world. And so as I was watching this happen, I was already in my mind trying to figure out how I was going to rationalize this clearly unrealistic behavior in the model when it came to writing the paper. And so I was, one day I was feeling kind of despondent about it. And I came across, I was just reading like some old papers, and I came across this map, this topo map that somebody had made of a Mima Mound field. And I was just staring at it and noticed, oops, that. So what you can see here in the magenta oval is something that looks like the cannibalization that we just saw in the numerical model. I saw that one, and then I saw this one over here. I was like, oh, wait a second. Not only does this look rare, but it looks kind of common. And I get goosebumps just thinking about this, but compare that with the model right here. So this is just a snippet from the model I just showed you. It looks exactly the same, right? It's just kind of flipped. The image is flipped, but this is absolutely uncanny. And you know, for a numerical modeler, this is this is the holy grail, where you've developed a computer model based on just a few simple rules, just a couple equations, and you end up discovering something about the real world that nobody had ever noticed before, and nobody would ever notice, would never ever be able to notice, because it takes so long. These things take thousands of years to form. And unless you discovered this in a computer model, we would never know about it. So again, this is one of those cool instances where the model shows you something completely new about the world. So qualitatively, the model looks like it's doing a pretty good job of simulating the real world and simulating gopher behavior and Mima Mound formation. But what about quantitatively? So we tested the model in a few ways. So the model predicts that after about 35 years, a mound should be about 25 centimeters high. And we can test that in the field. So this is the Carrizo plain. I showed you pictures of this area before. And you can see just a bunch of Mima Mounds everywhere. They've got the kind of the greener grass on top of them. So this area was farmed until the 1980s. And as a result of that farming activity, they had leveled these fields. These fields were perfectly flat. And then in the 1980s, this area got turned into a national monument. The farmers were kicked off. And since then, these mounds have slowly been growing and emerging from what used to be a completely flat landscape. So since I knew when these mounds had started to form, I could go out there and survey their heights. So here I enlisted my son. We went out there one December and surveyed a bunch of these emerging mounds. And since I knew, we were able to get their average height, I knew when the mounds started growing, I was able to calculate their growth rate, and found that after 30 years, they had grown about 24 centimeters. So I consider that a win. The model predicts that the mound heights should be, the final mound heights should be on average about 85 centimeters. When we measure these things in the field, the mounds range from about 0.1 to 2 meter high. So Also consider that a win. And then the final thing that we looked at was a spatial arrangement. So think about it this way. So imagine if the actual arrangement of the mounds looks like what we see here on the left side of the screen. But imagine that the model predicted that the arrangement of the mounds looks something like this. So kind of weirdly clumped with a few isolated ones. And so we needed a way to characterize the spatial arrangement of the mounds, so that way we could compare what we see in the field with what the model predicted. Because clearly, if if the spatial arrangement in the model was completely different from what we see in the field, then that's not a win, and that suggests that there's something amiss in the model. And so how do we characterize the spatial arrangement of the mounds? Oops. Well, one thing we looked at was the variability of spacing between the mounds. So we could have a situation where there's low variability of spacing. So in other words, the spacing is quite uniform. And at the other extreme, you could have a situation where there's a lot of variability of spacing between the mounds. So some mounds are very close together, some are far away. And so, high variability versus low variability. And you can also look at packing arrangement. So if you think of the way you could pack, say, spheres, you could pack them this way, which is known as square packing, because you can imagine drawing a square between the centers of the circles. And the other extreme when it comes to packing is hexagonal packing, which looks like this, where each row is offset from the other. So these are kind of the two end members of a packing continuum. And so we can plot our data kind of in this space where we have variability of spacing on the x-axis and then packing arrangement on the y-axis. And if you were to just take points randomly distributed in space, they would plot here along these two dimensions. Okay, so this is just, if you just randomly threw pennies on the ground, this is, and measured their spatial distribution according to these two metrics, they would plot somewhere there. The Mima Mounds from Merced plot here. So as you can see, it's kind of on the low end of spacing variability, and right in the middle in terms of square versus hexagonal packing. So that's where the Merced data show up. And then when we do the same kind of analysis for the model, it plots perfectly on top of the Merced data. Okay, so so in terms of the prediction of the spatial arrangement of the mounds, that's a big win. So to kind of wrap this up then, it's pretty clear that gophers build these Mima Mounds. The numerical model, both qualitatively and quantitatively, makes a lot of predictions that are borne out by actual observations in the real world. And another interesting thing about this is that it turns out that the Mima Mounds are the largest structures scaled by body size built by non-human mammals. So if you look at beaver dams, and when you think of things that are built by animals, beaver dams probably seem like the most obvious. If you scale a beaver dam by kind of beaver body weight, you get about a cubic meter of structure per kilogram of beaver. But for gophers, you get 100 times that. You get 100 cubic meters of structure per kilogram of gopher. Now, of course, it's kind of an unfair comparison in a way, because it takes thousands, it takes like hundreds of years to create a Mima Mound. But here's an interesting thing. Gophers are solitary animals, and so it's just one gopher per mound. So, it's each of those mounds that you saw was built by one gopher just occupying that mound. But of course, multiple generations over hundreds of years. And so that's it. Thank you for your attention.